It's a great honour to be here. Tonight, I'm going to talk about my career as an engineering geology consultant and, in particular, the lines of evidence approach and how this is important in dealing with complex problems. Now, as you've just heard, I'm not a researcher like many of the other Glossop lecturers. I'm not even a consultant with a particular sort of theme. I'm a general practitioner in engineering geology, and I suppose you could say I specialise in being a generalist. So before I start, I'd like to dedicate this lecture to the late Brian Hawkins, who's just been mentioned. It was Brian who got me into engineering geology in the first place. He was my PhD supervisor and my early years mentor. And I'm sure he'll be very proud that one of his former students is standing here tonight. Now, that's a picture of Brian standing in a gull underneath a housing estate in Radstock. Remember this picture because I'm going to talk about it slightly later on. First, a little bit of background. Now, in a recent recollection of his early days in engineering geology, Peter Fuchs wrote that by the middle to the end of the 1970s, engineering geology was a well-established discipline in its own right. Now, the end of the 1970s is when I started, and as you've just heard, Peter Fuchs was also my PhD external examiner. And he goes on to say that what happened in the following decades is another story. So I thought I'd pick up there where he left off and make my story that other story. So this is my timeline of important engineering geological events. And you can see that by the 18th century, William Smith has effectively founded was the subject of engineering geology. And then in 1963, the engineering groups formed. A year later, Skempton gives his publishes his famous lecture on, paper on residual shear strength, a subject very close to my heart. I met Skempton once. I was a young engineering geologist, and I was going to be one of the rapporteurs at the engineering group conference in Edinburgh. So I went to Imperial to see John Hutchinson because he was going to be the chairman of the session. And when it came to lunchtime, I said, I'll have to buy him some lunch. And he said, would I mind if Skempton came to lunch with us? Because apparently he always had lunch with Skempton. I don't mind having lunch with Skempton, that's fine by me. So. Anyway, Skempton bought his own lunch because I got there a bit too late, but nevertheless. 1977 comes along, and there's me starting my PhD in a well-established engineering geology setting. And then 20 years later, Peter Fuchs gives the first Glossop lecture, and here I am, 21 years after that, giving the 19th. Before I move on, I'd like to say thank you to various organisations who I've worked for, and in particular the people I've worked with, as you've just heard, many of whom are here tonight, for so many opportunities and experiences over the past 40 plus years. And there's 4 companies in the bottom left-hand corner who I'm lucky to have information for this lecture. Special thanks to SRK and to Hydrogeological because they are co-sponsors tonight amongst the other sponsors. Now, some of you will know me as a traditional engineering geologist. Some of you will know me from the field of contaminated land, but when I started in 1977, there were no hats. And since 1990, as you can see on the top pictures, since 1990, I've had 2 hats. And that was when I first got into contaminated land, when we were constructing the Gateshead Garden Festival site. And tonight I'm going to be wearing the engineering geology hat, metaphorically speaking. Anyway, moving on to the lines of evidence approach. Strikes me that there are 3 interlocking themes that an engineering geologist uses when working out what's going on at a site. And they are firstly multi-disciplinary working, second applying a wide range of knowledge and experience, and third, learning lessons from the past. And the first theme is multidisciplinary working, and by this I mean working with other professionals, your own variety of technical skills, working with various other stakeholders in the industry, and appreciating the different needs of projects in different industry sectors. And this is a word cloud of some of the disciplines that I've been involved with over the years. And there are ever more specialisms, and we certainly need non-specialists to bring them together. And I think the ideal person for this job is the engineering geologist, but not just as a project manager, they must try to aim to be a high-level technical thinker capable of working in multiple disciplines. And I'm sure we all know the IAEG definition of engineering geology, but it was Jim Griffiths, the 14th Glossop lecturer, who reminded us at the Engineering Group Cambridge conference earlier in the year that engineering geology is not a sub-discipline of geology, it is in fact the application of all of geology to engineering projects. This is a quote that dates back to 1950. And I think engineering geology is multidisciplinary at two levels, at the level of the project and at the level of the individual practitioner. And the second theme is knowledge and experience. This really means all your technical and non-technical skills derived from education, CPD, on-the-job training, and the sheer number and variety of projects that you've been involved with over a career. And the important thing here is it depends on who you work for. It depends on the kind of job that your company gets, and it depends on the problems that those particular clients have. So everybody is probably different. Now, my own experience started in 1977 with my PhD, as Matt's just told you. I was using engineering geomorphological mapping, which was a relatively new topic in those days. The first UK maps had been published about 1972. And I was one of the early adopters who used it to look at superficial structures, as this example of a cambered spur in the Swainswick Valley in the South Cotswolds. Now, this started as a Brian Hawkins consultancy project, looking at the A46 rerouting, and it rapidly sort of became a larger research project for me. Now, I'm going to be returning to this locality towards the end of the talk. Another thing that came out of my PhD was a weathering scheme for the Fuller's Earth. Now, this was really just the next phase on from the mapping, because most of the landslides I've been looking at were on the Fuller's Earth. And it was also, to a certain extent, a child of its time, because at about that time, other people had been producing similar schemes for the London clay, for the Oxford clay, the Lias clay, the Mercia mudstone. So mine was just one of a list at that stage. And also at that time, the Bromhead ring shear device came on the market, and I bought one of the earliest ones. Eddie probably still remembers the serial number, and I got involved in looking at how the curve of the envelope at the low shear stresses can be important. And I also used it to look at the relationship between calcite and Phi-R for the different weathering zones in the Fuller's Earth. And did you know that Eddie's paper from 1979 has recently been shortlisted as one of the best 5 ever papers in ground engineering? I hope you all voted for it. We'll find out next month who won. And my classification of gulls, that came about simply because of a phone call from a housing contractor who'd found a hole in the bottom of a foundation trench, rather like the one at the top right-hand corner of this picture. Remember the picture of Brian? Well, at the beginning, we climbed down a wire rope ladder into a hole just like this, and it had been discovered by one of the workers early in the morning. He was a caver, and he'd been down and explored, and he'd been told off by the site manager for breaking some sort of health and safety rule or something. But later on, he was praised for actually finding this. Now, you might see there's a certain amount of randomness in my career already, and this carried on throughout my working career. I basically work with whatever my clients want me to do. Now, in the 5th Glossop lecture, it was Dennis Brunson who introduced the concept of the geo-team roulette wheel. Well, I'm afraid mine's a bit more down market. It's engineering geologist dartboard. So here's the list of topics again, and I'm sure you know what's going to happen. Quite often when I went into the office, I hadn't a clue what I was going to be working on that day. A bit like throwing a dart, what's it going to be? Landslides, or maybe it's superficial structures, maybe it's contaminated land, maybe it's all three. I'm sure you get the general picture. But the key is actually diversity. And based on H.H. Reed's famous quotation about best geologists being the one who's seen the most rocks, surely the best engineering geologists are the ones who have developed the most conceptual site models. And if there were to be a prize, I'm sure the prize would go to Fuchs. Here are a couple of examples of varieties of model from the same information that he showed in his first Glossop lecture. And the third theme is lessons from the past. And you need very good research skills to be able to learn from others, basically so as you don't make the same mistake twice, you don't reinvent the wheel. This means conferences, mentors, meetings, papers, this sort of thing. And a very good starter, when you're stuck with a new problem, is to look for case histories. And I urge you all to write up more case histories. Now, there have been a number of milestones in the lead up to this lecture that's helped sort of sharpen my mind a bit. The first being the 200th anniversary of William Smith's map. This was celebrated in Bristol by Hydrogeological with a series of public lectures. And then there was the EG50 conference, which celebrated the 50th anniversaries of the QJEGH and the teaching of engineering geology at Portsmouth. And then later this month is the 50th anniversary of Grand Engineering magazine. And the picture on the bottom shows us on the engineering group Kent Field trip. We're standing beside the A21 Sevenoaks bypass. And this is where in the 1960s it was realised that on shallow slopes, maybe 3 degrees, with relic shear surfaces, you can reenact reactions when you actually start excavating, causing havoc for road construction. There's one of the shear surfaces at the bottom. Now, this is, to my mind, where it all started. Hawkins taught this in his third-year undergraduate course. This is hallowed ground, to a lot of the older members on this trip. We were on a pilgrimage, but it rapidly became apparent that the younger members of the group had never even heard of some of these papers, So this is probably one of the reasons, I think, why Dave Giles and others re-established the engineering group conferences after a gap of about 12 years. And the last one was, or the latest one, beg your pardon, was in Cambridge this year with the theme of keeping lessons alive. Now, these three themes could be thought of, if you like, as some sort of lines of evidence toolkit, because lines of evidence are fundamental to the conceptual site model. The past is the key to the future, because if you know what's going on, you stand a better chance of predicting engineering behaviour. We all have to educate our clients as to the ground risks, and my advice is don't cut corners, take time and think about it. Complex problems require multiple lines of evidence to reduce uncertainty and risk. And it's probably true to say that the more complex a site, the more lines of evidence are required to give you the adequate level of confidence. But you have to know whether a site is a simple site or a complex site. If you don't think, you get the wrong answer. And remember, the conceptual site model is what underpins all the advice given to other stakeholders and clients by engineering geologists. I want to move on to three case histories which really illustrate the lines of evidence approach in different circumstances. Now, for those of you who are expecting a contaminated land one, I'm sorry to say I did prepare one, but it frankly had too many graphs for this evening, and you don't look like the kind of people who like looking at graphs. So it will be in the published paper. It concerned an oil leak of something like 9.5 million litres into a principal aquifer. And the original consultants on the site basically hadn't understood what was going on because they had a too simplistic ground model. And SRK came along and we re-looked at it, and through a number of lines of evidence managed to understand the basic science. The physics was actually going on in the aquifer, and therefore were able to propose workable remedial measures. Okay, so moving on. The first case history is an example where there was no standard approach to do something because, as far as we were concerned, no one else had done this before. And it concerns decommissioning of cryogenic gas tanks in Canby Island. And as you heard, my first job was with Sir Robert McAlpine and Sons. I was the only geologist working for the company. I was a sort of internal consultant, really. I used to work on all sorts of things: designs, contractors' alternative schemes, site problems, contractual claims, a bit of research, materials, concrete technology, anything that was going. And in fact, the most weird query I got was from a guy who had a tower crane on site, and he wanted to lift an air conditioning unit onto the top of a brand new office block in central London. It didn't quite have the capacity to lift this, so rather than close the road and get in a mobile crane, he rang me up and said, if I attach a helium balloon to the end of my jib, would that give me the extra little bit of lift? So I did the calculations and pointed out that it was in the Heathrow approach, and probably you wouldn't get permission, so he hired the crane. Anyway, one of the very first jobs that I took on was from my predecessors, was this cryogenic gas storage problem. 4 tanks had been built, 40 metres by 40 metres, in the 1960s by ground freezing, basically creating a 6-metre thick ice wall and an 8-metre thick ice plug. You excavate out the unfrozen ground, put an insulated top on, and these were then filled with liquid petroleum gas that was imported from Algeria. But they proved not to be very economic, mainly because of the amount of leakage. And additional problem was that the ice kept getting bigger and started to threaten some of the other installations on this site. And so by 1977, they put steam injection pipes in the ground to limit the spread of the ice. So clearly not a very eco-friendly thing to do. So it was decided in 1981 to get rid of the whole thing, decommission them, fill them with sand. McAlpine's got the job, and it's about 400,000 tonnes of sand were required. It was calculated that the ice walls would take about 90 days to melt, so the filling had to be rather rapid. It was also the problem that no personnel were allowed in the area because of the risk of explosion, because there was probably some gas still remaining in the ground, even though these tanks had been purged with nitrogen. And the other problem was no access by road was allowed for deliveries because it was a residential area, and so everything had to come in by sea. So the sand was dredged from the Thames estuary. And this is the general setup showing this remote filling gantry on the rails with the various conveyor systems coming over the top of one of these tanks. And my job was to sort of help work out the method of working, which basically meant take engineering geology concepts and think laterally, think quite laterally. Typical questions we had to answer, and I won't give you the details, the technical details are in the paper, but at minus 100 degrees C, how would wet sand behave? What would the angle of repose be? So how many filling points would you need? Would the sand freeze before it hits the base? Would this affect the settlement? What would the settlement be? How much sand would we need? Would we need to top up afterwards? And the sand we were using had an optimum moisture content of about 15%, but in the stockpiles it drained down to a field capacity of about 8%, so we were using it dry of optimum. So was it actually going to self-compact? And the big question was, how much do we buy? This is the contractor's risk here. We were buying wet sand from a dredging contractor by the ton, but we were using damp sand by the cubic metre. Now, if we didn't have enough, it was going to cost an awful lot of money to mobilise another dredger just for a small amount of sand. If we had too much, we couldn't get rid of it because we couldn't take it out by road. So it was quite a problem. Anyway, here's some pictures just to show the scale of what was going on. On the top left, there's the jetty and the dredger and the conveyor system. Below that is the stockpile. And on the bottom right, they've just finished one of the tanks. You can see they're starting to take the roof off. At that time, you could get in and you could see the ice wall at the top in the middle picture. This was a very early job, as I said. It was one of the first that made me think that if you do a decent amount of research, you do some proper laboratory and field testing, including we're mucking around with liquid nitrogen and all sorts of things, you can actually complete a job successfully, even though no one's ever done it before. And the second case history, this is again a McAlpine project. This is one I spent a lot longer working on. And in this case, there was a standard method of doing things, but it wasn't going to work for us, so we had to come up with a new way of doing it. We were trying to use chalk to create a marina near Portsmouth. And the lessons from the past concerning chalk tend to get published every 12 to 18 years, and this was something that has developed during my 40-year lifespan, what do you want to call it, timeline. First symposium was in 1965, and then when I started, what was current was LR 806, which had come out in 1977. And this basically divides chalk into different classifications, and it gave you advice as to what you could do with this chalk in the summer, in the winter, etc., in terms of creating earthworks. And then this was current in 86, when McAlpine got the job to build this marina infrastructure, which had up to 5 metres of compacted chalk behind concrete retaining walls. And then in 89, Roy's International Chalk Symposium came out, and I do have a paper on this subject in that volume. And then carrying on since then, the Syria report was out in 2002, and only a couple of months ago was Chalk 18. This is an aerial view on the right of the project. There's about 500,000 cubic metres of fill. behind 2.2 kilometres of concrete wall. And the project was basically to dredge a sort of tidal lagoon just alongside the M27 before you go into Portsmouth, get rid of the alluvium, and that left a formation of structureless chalk, probably soliflucted, with an artesian groundwater with a head a metre above the formation level. Now, the picture on the bottom shows the site, but you can see in the background the quarries in the Portsdown Hills, is Paul's Grove Quarry, and so chalk was the obvious choice for the filling material. But because we had to tip the chalk in water in the winter onto a soft formation, the standard methods of working weren't ever going to work. So we had to come up with some sort of thick layer chalk specification with minimal compaction to try and preserve the lump structure of the chalk, and thereby use it more like a rock fill. And just to add a bit of spice to this, the housing contractor, who was a different organisation, we agreed that they would be able to build their houses on normal unreinforced strip footings without any, on 5 metres of fill. You're all laughing, but that's what you did in the 1980s. And I haven't fallen down as far as I know. I did Google, but I didn't find anything. So if you know anything about it, keep quiet. So we needed a number of lines of evidence to actually be sure this was going to work. So I did a literature survey. I went to speak to other people who'd used chalk in a sort of similar way. And there were quite a few, because this wasn't actually a new idea. It had been around for sort of several decades. And the obvious person to go and speak to is Rory, the future 11th Glossop lecturer. Gave me a lot of help. And then we did a couple of phases of site investigation and a lot of testing in the laboratory in consultation with the approved supplier. And not only did we do the standard sort of lab tests, we did some large bench scale tests. So the one on the left here is a fines washout test. We're trying to predict what the rainfall would do over 100 years of seeping through this chalk. And the one on the right is a flooded plate load test to see what effect the tide cycling up and down would have on the allowable bearing pressures. Then we went out on site and did a trial excavation and embankment, and from that we developed this thick layer specification. Then we constructed it, and during construction there's an awful lot of verification testing, and that included a couple of, or several actually, trial foundation loading tests, and one of them had a tidal cycling built into it. And I'm going to talk briefly about these two in the red. So the first one is the trial excavation embankment. There are 3 future Glossop lecturers involved in this project. There's a young David Norbury inspecting the formation. And because David didn't sink in up to his waist, we then all went onto the formation and realised it was all right. And it wasn't going to be as bad as we thought. And the water wasn't coming in quite so much as we thought either. So we placed 3 1-metre diameter settlement plates on the formation with rods attached to these plates that came up to the top of the fill, sleeved by a plastic sleeve, so we could measure settlement. And as we were filling, we started levelling these rods, and therefore were measuring the settlement underneath. And when we got to the top, we set a number of surface settlement pins into concrete, so we could measure the top and measure the bottom, and then by difference we could measure any internal settlement of the fill material. And here's the work in progress. The first metre was actually just dozed into water, and then the next 4 metres were placed in 600 mil lifts with 6 passes of an 8-ton roller. And that's the finished project at the bottom. And it turned out that virtually all the settlement was in the natural ground, and all of it was practically immediate. So we had 29 millimetres of settlement after the first 5 days, only 32 after 236 days. And this is the trial foundation test. We produced 2 different sizes of foundation and loaded them with water tanks, and then measured the settlement with precise levelling techniques. This is the first test, and you can see it's surrounded by a sheet pile cofferdam. We dug a couple of holes in the corner. We could put water in, pump the water out to simulate the tide going up and down that was measured with a series of piezometers. We also dug a trial pit down the outside and burned a hole through the steel to mimic one of the weep holes that you would get in the final concrete structure. And the little jars there are samples of water that we collected, and the numbers on the top, the time in minutes since the flow started. So you can see after about 5 minutes the water is running through clean, and we didn't anticipate any significant loss of fines. The settlements, they were all less than 10 millimetres, so a very good result. And I thought I'd just show you this. It doesn't matter whether the water was coming or up or down or whatever, there was still only 10 mil max. But this is a page from the original report, and it just shows you how far we've come since the days of the good old Epson dot matrix printer. And here's the site today, all very gin and tonic. As I say, I don't think it's fallen down. Multiple lines of evidence did produce a workable solution. It was a collaborative effort with all the people involved and a very successful construction. And this case history is one from later on in my career, and this is an SRK Hydroc joint project. It's a landslide problem trying to resolve the mode of failure of a landslide. And it revolves around an oil company who leased a site on the Isle of Portland to build an underground gas storage facility, only to be told when they applied for planning permission by Dennis Bransden that they were on one of the UK's largest active landslides, and did they know this? And of course they didn't, so hence the panic. And if you look at this picture, which is taken from the northeast, the whole of the ground below the plateau there is one large landslide complex. Now this is the site outlined in red. It's known as HMS Upper Osprey. It's a former naval base, shore base. And on the right-hand side you can see a large oil industry drilling rig surrounded by the rubble of the demolished Navy buildings. Now all that undercliff area is all one large landslide complex. And you can also see against the cliff, the Portland Stone Cliff, there's a large scree slope, and that is waste rock tipped over from quarrying activities on the top. And the project then was to actually create 14 caverns 2.4 kilometres below the site by solution mining a layer of salt from the Trias. And it would hold 1 billion cubic metres of gas, which is about 1% of the UK annual demand. And the idea was to try and even out supply and demand in the winter and try and reduce reliance on imported gas from Russians and elsewhere. And there were going to be 2 wells per cavern, one for gas, one for brine. And the idea was that the caverns are filled with gas in the summer from the national grid, which is about 37 kilometres onshore in Dorset. And then the brine that was in the caverns would be pumped out into brine compensation wells in the Triassic Formation about 18 kilometres from the site. Then in the winter, the gas was pumped back out into the grid for use, and to stop the caverns from collapsing, because the gas had been in there at 400 atmospheres, you had to put the hypersaline brines back in from the compensation wells. And this was going to be about a £500 million job at 2008 prices, more like 660 million at today's prices. This is a schematic of the 14 wells and 14 caverns and 28 wells that were going to be produced by directional drilling methods. And at the top right is a little cartoon showing you how these are constructed. It's quite simple, really. All you do is pump water in one hole, it dissolves out the salt. You take the brine out of the other side, and by balancing these two, you keep the concentration right, and you create a void, which is probably easier said than done. And any sediment just settles to the bottom. The geology of the Isle of Portland is a very simple dipping sequence with the Portland stone at the top, and below that is the Kimmeridge clay formation, which is on which the site sits on the side of the slope. And you can see from the geology map, the outcrop of the Kimmeridge is all shown as landslide. And this landslide debris, plus a little bit of worked ground, I'm calling colluvium in the following slides. Now, at the time of the original planning application, the only ground model was one that Brunsden and others had published about 10 years previous. It was based on similarities to certain sites in Italy. And this is very hypothetical. They hadn't done any drilling or anything, and they freely admit that. But what the model suggested was that the weight of the Portland formation, the Portland sand, the Portland stone, was actually causing it to sink down into the Kimmeridge clay. And this was then causing lateral spreading, ductile flow, and at the coast, this gave way to deep-seated rotational failures. And there would be large blocks of this limestone sinking in, foundering into this ductile layer. Now there is, down the centre of the isle, a depression. And this depression was cited as evidence, or one of the lines of evidence, that this was happening, and it's this sort of sagging into the Kimmeridge Clay. Now, if you're going to build a deep gas facility on an active landslide, you've probably got two aims. The first one is to minimise the volume of gas in the wells and in the facility in the event of a large-scale massive failure, because you would probably get a blowout and that would probably flare off and you'd have a large explosion. The second thing is, even if you don't actually have a large failure, you've still got quite a lot of ground creep movements, and therefore you need to make sure that your surface plant is designed to take into consideration that creep, particularly if you've got gas in pipes at 400 atmospheres. So the problem then was to work out what is the deepest level of landsliding that is credible on this site. And all these sites are protected. There's a lot of these in other parts of the world, particularly Germany. So there's, it has been done, not necessarily on landslides, but they have a subsurface valve that shuts off automatically if there's some damage to the wellhead. And what was going to happen here was it would be connected to some monitoring software that would detect landslides, and in case of landslide, the wells would be clamped shut. But you can't just be overcautious, because if you make these things too deep, you've got a much bigger volume of gas in the pipework that's going to flare off, and you're adding to the hazard and adding to the potential risk of explosion. Clearly, if they're too shallow, then the thing doesn't work. So we really had to work out where this red line was. So basically, the objective of the project was to produce detailed evidence to support the permitting for what was quite a high risk financially and safety project. And therefore this boiled down to we had to either find or prove the absence of ductile flow and lateral spreading leading to regressive deep-seated rotational failures. And to do this, particularly as we're trying to prove a negative, multiple lines of evidence are required. There are 15 listed here. I don't expect you to read them all, but I'm just going to go through briefly some of the things we did to give you a sort of flavour of the site. First thing we needed was some contours, and we got these from a LiDAR survey plus bathymetric surveys offshore. This enabled us to start plotting up our desk study information, and it also would give us a base for site investigation and future cross-sections for detailed numerical stability analysis. And this first line of evidence is actually quite interesting, because even this started to point out that the landsliding might not be as deep as anticipated. Now, if you look at the section at the top, this is Brunsden's sketch, no scale to it, done by eye, shows these deep-seated failures. But if you actually have the real contours, as you do at the bottom, you see the slope is much less. It's only about 15 degrees. Now, I started to try and sketch in some deep-seated failures by eye. You can see on the left-hand side of the model at the bottom, it looks reasonable. When you get to the right, it's just kinematically not feasible. There's no way that that slide is going to sort of do that. So this was an early indication that we were going to have to prove a negative. The desk study brought out lots of past history of landslides, including this map on the left, which comes from a Brunsden paper. And the most significant was said to be the 1792 East Weir landslide, which is about 2 kilometres long, and according to Brunsden was the largest recorded landslide in the UK, in sort of living recorded memory. And one of the contemporary accounts referred to rocks that were some depth under the water being raised above the water. Now this was taken to imply that there was a deep sea rotational failure and sort of toe heave, and the rocks were sort of shoved up at the bottom of the sea, which led to this original model. We also found the oldest map we looked at was this one from 1710, which shows the site. And there's a little thing underlined in red, you might not be able to read it, but it refers to earth rolls on the site. These are caused by the tipping of quarry waste over the top, as you've seen from the aerial photograph. Now, these quarries were the ones that were used to rebuild the city of London after the Great Fire in 1666. Looking at some slightly more recent documentary evidence, these are some aerial photographs from the 1970s, and you can certainly see the old Navy buildings, and you can see some of the works that the Navy put in. That includes coastal protection, rock armour. It includes some deep drains that addressed particular known landslide areas. And you might be able to see some faint lines, parallel lines in the vegetation. This is a series of land drains. And you can see the scree slopes at the top. Now, despite all this work, there were still small-scale slips there during construction of a little highway embankment by the Navy. There's a landslide forming on the top left-hand corner. Now, just to the west of the site is an underground facility for bunker oil storage. Now, this is a facility that used to be owned by the Navy, is now in private hands, and it has an access tunnel with a cast iron lining. And this cast iron lining is cracking at one point in the tunnel, or one little zone along the tunnel, and they're extensional cracks, and the present owners have carried out some investigation work. And you can see on the cross-section the little red ticks. Those are inclinometer readings where there's a shear zone, and you can see there is a shear probably running along the base of the colluvium. And what appears to be happening is the colluvium is gripping the tunnel and sort of pulling it out from the hill and causing extensional cracking at that interface point. We looked at the standard stereo air photo interpretation, and you can see this is my effort at it. There's quite a few little landslides down by the coast, some bigger slips and the scree slope right at the back of the slope. And the whole of the development site, which is outlined in red, probably one large landslide unit, obviously modified by human action to give you a nice level building site. People always build on landslides because they're nice and level, the bit that's moved. So this is just one of those sites. And Malcolm Whitworth did some engineering geomorphological mapping for us, and he came up with a number of different zones of landslides across the site. But he also went up into the limestone quarries and looked at the cliffs, and he was trying to work out whether there was any offset in any of the bedding that might indicate this sort of sagging into a ductile layer, and he found no such evidence. We did a site investigation next, about 8 boreholes in the sea, 53 boreholes on land, up to about 100 metres deep. And these were designed to give us a large, high-quality 3 section lines to work on for stability analysis. And they were also some boreholes in between there, some sort of general infill geotechnical design boreholes. And we were alerted to a chap called John McLaren by Rodney Chartres. John had worked with Rodney in the Property Services Agency, which was the government body that looked after the estate for the Navy at that particular time. And McLaren had done an MSc at Surrey University, and this is some of McLaren's data. He'd put in some inclinometers, and you can see on the map on the left-hand side the vectors of movement for these inclinometers. And the largest movement was the one in the insert in the bottom right, which was 69 millimetres over a period of 5 years. And this is a little landslide just in front of the site on the coast. And if you plot these shear zones onto the modern cross-section, you can see that all the shear surfaces were roughly coincident with the base of the colluvium, top of the Kimmeridge clay. We put our own inclinometers in, and we had a few months in which to monitor these. And we got movements probably mostly within the 10 to 20 metre depth. McLaren had also put in a number of movement survey centres to measure surface creep, and these are 6 metre long concrete piles that were pushed into the ground in rows. So you could stand on the top of the cliff, and there was a base station up in the quarries, and he could survey the movement of these down the slope, and it was done once every 3 months for quite a number of years. And again, those displacement vectors are there, but the largest one is highlighted at the bottom, exactly the same place, number A6. And it moved 94 millimetres over a period of 5.5 years, so slyly moving into the sea. And these are McLaren's data plotted for line A, the line that had the biggest movement. So at the top is base station A1, at the bottom is A6, the one by the sea that moved the most. And the top line on that graph shows how after 1979 the rate of movement actually declined. And it stayed roughly the same up until 1993 when they stopped monitoring it. The same goes for A2 and A3 and A4 and 5 further down the page. Now, we managed to find A4 and 5 and A1, and resurvey them in 2006. And interpolating the lines, you can see the blue and the green line there. They're very much similar to what had happened since about 1982. So the rate of creep had been the same all along. This is about 3.4 millimeters per year. The next line of evidence was some shallow resistivity work, some resistivity profiling. Basically anything that's not dark blue was deemed to have moved, so it was the colluvium and the made ground, sort of more disturbed material in terms of its resistivity profile. Now, that red line is the final red line that we came up to, which was the top of undisturbed Kimmeridge clay. But at the time this work was done, we obviously didn't have that line, and it looked pretty quickly that there was some sort of deep-seated rotational failure, probably in the top third of this slope. So we put a lot of boreholes in that area and found actually it wasn't disturbed, it was undisturbed. And the geophysicists went back to site and discovered that there was actually some reinforcing steel in a concrete slab, so this was giving a false positive. But more interesting, perhaps at the bottom of the slope, there's also an indication of a rotational failure, and this was underestimated by the geophysicist. This was a negative anomaly caused by saline intrusion. So I think the conclusion for this particular line of evidence is probably fairly ambiguous. But what was much better was the geophysics from the seismic profiles. Now the client had a number of seismic profiles shot offshore, and you can see that the Isle of Portland there for scale, quite a large site area here. And by combining this data with a number of other data sets from BGS and other organisations, the modelers were able to produce a 3D model based on structure contours on a number of particular marker beds. And the picture on the right-hand side is an oblique view of the site showing the top of one of these markers. And on the left-hand side is a plan showing the structure contours on the Portland stone. Now you can see there is a shallow dipping syncline coming down the middle of the isle, but it's actually part of a much bigger syncline that goes off to the southeast. Now this continues to depth, so if you follow this down into the Triassic, you can still see folding, and those little red blobs are where the caverns are going to be. And so this really showed that this depression down the middle of the Isle of Portland, it wasn't to do with the stone just sort of sinking into soft clay. It was actually a original tectonic deep-seated feature. So turning to the Kimmeridge clay itself, it was Remus Galway, who was also working on the team, who pointed out that not all the cliffs in Dorset where the Kimmeridge clay is exposed are crawling with landslides. And here are some very nice examples of what looks like very competent mudstone sequences. And you can see quite a number of marker beds in here. And so we thought, well, if we could trace these marker beds below the site in the boreholes, we would be able to work out more or less where ground is had moved and where ground is that was still in situ. This is Remus drying the core out in the sun prior to his detailed stratigraphic logging. Now, Remus had been involved with and probably invented the stratigraphy of the Kimmeridge in the North Sea oil fields, and he'd recognised something like 63 stratigraphic zones, and 28 of these are present in the Dorset section. We found a number of interesting things like whole ammonites in borehole core, but the most interesting thing from the project was actually these very thin white bands. Now these are coccolith bands. They're representative of former algal blooms, and they're traceable across tens of thousands of square kilometres across the outcrop of the Kimmeridge. But these are 3 boreholes from across the site. And you can see they line up almost millimetre accuracy. It's like some sort of natural barcode. Now picture missing there. There should be a picture on the left-hand side. It was there earlier. But anyway, the picture on the right is a detail from the picture on the left-hand side. And it basically shows that we have also done some downhole geophysics. And this is a natural gamma log. Means you don't have to rely on the good old-fashioned stretchy driller's tape measure to work out where you are. So you can actually find out where these layers are in a good 3D space. And they match up very well, as you can see from this particular section. Now this allowed us to produce structure contours, as here on the right-hand side on this little plan, on the various marker beds. This one's known as the freshwater stepped stone band. And from that, we could then reconstruct where these bands are under the site. And basically, anything below the green line was natural, in situ, undisturbed Kimmeridge clay. So we're getting somewhere. But Reimers, in his mapping, he identified 3 zones of disturbed Kimmeridge clay. Now, this is written up elsewhere. I'm not going to bother you with the details, but Zone 2 was perhaps the most enigmatic. This was highly disturbed with bedding degrees up to about 70 degrees, full of shear surfaces, big basal shear surface at the bottom of the unit. Now, if you go along the coast a little way, you can actually see it in the outcrop. And Rob Smith is standing here with a lightsaber demonstrating where the bedding dips are. And you can see it's quite dramatically over short distances. And a couple of mechanisms were postulated. One is something that had been seen a few years before in Lyme Regis, and it was put down to shallow translational slides in an active layer of melted permafrost in the summer, creating sort of noses of fold structure. Later solid fluxion sheets coming over the top. Reimers favours something he calls periglacial creep folds. These are much larger scale. And again, small incremental movements in an active layer in the summer. But here the material is just deforming plastically and without breaking up. So that's the potential mechanism, although perhaps slightly academic. Now, we also needed a hydrogeological model for stability analysis. It turns out the groundwater around here is fairly discontinuous. It's not seen as sort of standing water in pits and boreholes where you can just join the dots on a map and produce a water surface, although clearly it is there when you turn the air flash on after a break. So the hydrogeologist resorted to sort of water balance calculations and tied us into a mod flow model to come up with a prediction of the groundwater heads, which is one of the pictures at the bottom here. And it basically turned out that the groundwater level, the phreatic surface, was very close to the base of the colluvium. And we used this as part of a sensitivity analysis, looking at what was going to happen in the future with sea level rise and climate change and things. But this was the starter for 10. So putting all this information together, we were allowed to produce a revised conceptual site model. And basically everything here that's light blue is undisturbed Kimmeridge clay. And you can see it's got quite a stepped profile. And that's put down to marine erosion over several different stages of sea level. And the red there is the Zone 2 Kimmeridge. Now, this is a periglacial feature. Some deposits are just trapped on a little ledge, on a little bench in that zone, a little bit slightly further upslope. And the yellow is the colluvium. That's come over the top. It's got shallow translational failures in it. And you can see that the wave cut platform goes quite a long way out to sea. And it's very shallow, and in this particular section, it's about 300 metres the colluvium extends out to sea. So it's quite feasible that if you had quite a large, shallow translational slide, you'd get some sort of bulldozer effect, and you could easily conceive that the material under the sea could be pushed above sea level. So you don't actually need a deep-seated rotational toe heave to create the sort of thing that was seen in 1792. And from that, we went ahead and we did some slope stability analysis using the normal sort of limit state stuff and also some FLAC modelling. And the FLAC modelling vectors, as you can see on the bottom section, they all seem to occur quite nicely in the colluvium. We couldn't, however we tried, get any ductile flow in the body of the Kimmeridge clay formation. So, putting all this together in the multiple lines of evidence, we actually came up with no evidence for ductile flow. So the central depression is actually tectonic. There's no vertical offset of any of these limestone blocks. The Kimmeridge is in fact a competent mudstone. There's no vertical displacement of any of the marker beds that we could see, or thinning of these marker beds. This Zone 2 is just a remnant preserved on a buried topography, not actually a ductile layer in itself. There's no evidence of ductile flow from the bunker tunnels or from the FLAC modelling, and no evidence of preferential displacement within zones where there are lots of shears in the Kimmeridge. And similarly, we found no evidence for deep-seated rotational failures. The undisturbed Kimmeridge is relatively close to the surface, maybe 20 or 30 metres. A stepped, buried cliff line has been refined by complex landsliding during one or more cold climate periglacial periods. And modern landslides seem to all have occurred in this disturbed strata, with the movement since 1970s being restricted to surface creep, held back probably by the beach protection and the slope drainage works that still seem to be functioning. The movement there broadly coincident with the base of the cluvium. So the seabed contours show only a modest toe debris would be proud of the water in some kind of horizontal slide, as I've just explained, a sort of bulldozering effect. And repeated shallow translational slips have buried an old cliff. It's now being exhumed by marine erosion, prompting reactivation, and this is seen up to 300 metres offshore. And the results of all this, when put together, you could build this facility. You'd need a certain amount of engineering to cope with the creep, but that wasn't difficult. And the good news was all the planning applications and the hazardous consent applications were all agreed in May 2008. But the bad news was the client couldn't raise the capital. No one was going to put their money where their mouth was. And so unfortunately, this project remains unbuilt. So we'll never know. But anyway, so I hope those three case histories have sort of given you a clue what you can do if you actually stop and think about a site. And that got me thinking. I think, well, should I go back to my original Cotswold mapping? Can I update this with new technology, as Johnny's just been explaining to us? And can I get additional lines of evidence to add to my historic data set? So this is my mapping area, just north of Bath. You can see the Avon Valley going east to west. The Swanswick Valley goes off to the north, and this contains the corridor for the A46 I mentioned earlier. And I want to briefly look at three landslides, one in Soper's Wood, one in Balebrook, and one in North Stoke. Now this area is a shallow, regional shallow dip. It's a desiccated terrain with a limestone cap rock and silty, sandy material and clays in the valley sides, which are all prone to frost susception and therefore cold climate, superficial structures, superficial deposits. The geological map shows in yellow the great oolite on the tops of the plateau, and then round that with the hatch shading is the Fuller's Earth, which is a landslide deposit. Below that's the inferior oolite, and then below that are the Bridford Sands and the Durham Formation, these sort of silts and sands. And the bottom of the valley is the purple, which is the lias, the Charmouth Mudstone Formation. Now this is the sort of cartoon section off the bottom of the BGS map. Shows you all these things that you can get around here. There are cambers, there are gulls, there are shallow failures on the side of the upper slopes in the Fuller's Earth. There are deep-seated failures in the lias on the lower slopes. There's even a valley bulge, and this is a photograph of the valley bulge that we took on the 1995 engineering group field meeting, which I happened to organise. We didn't know this was going to be here. It was just a temporary exposure in a road cutting. I put this photograph particularly in for Jeremy Hucker, who's in the audience tonight, because he didn't go on a field trip. He decided to go and see Torvill and Dean ice skating instead. So bad news, Jeremy, wherever you are, but this is what it looked like. Anyway, this is Chandler's map of the section of the valley. This is done to 1-to-1 scale, so you can see what's going on. You can see the bedding coming from the right down to the left-hand side. It's dipping to the left and it's getting thinner, and that's not supposed to do that. That is cambering. It's supposed to be horizontal and the same thickness right the way across. So that's the effect of cambering. And you can see here on the surface is a very thin layer of mud flows on the Fuller's Earth, and that's the location of the Soper's Wood site. And then down in the valleys at the bottom in the lias are deep-seated rotational failures, probably cut by the Avon and its tributaries when the ground was probably still frozen. The Balebrook and North Stoke being good examples of those two slip types. This is the upper slope, and this is what it looks like when you get on the upper slopes. This is full of landslides, but they're quite degraded, and you have to get your eye in. But a more obvious site is this one known as Soper's Wood. It's become a bit of an iconic site in that respect. It's not really the wood, it's actually the field just to the southeast of the wood that I've circled here in yellow. And just to show you that the top right-hand picture is the sort of air photo that was available to me in 1977. It's pretty crummy, it's black and white. You can't really see what's going on. I didn't really use them for very much. But even now, with upgrades like Google Earth, you can download for nothing much better images, and you can clearly see the mud flows in this 1999 image, which is the best one I found from the historic data set, because you can see it's got a very low sun angle. And this is the field in 1978. Again, it's at a low sun angle, not much grass. This is in the winter, and you can see all these mud flow deposits in the grass. They're not very big. I mean, the relief of these is usually much less than a metre, or there are a couple of larger ones. They do actually show up much better if you look at them in false colour infrared, because you get a much better contrast between the pink grass and the sort of light bluey grey soil underneath. And that's what they look like on the field. This is, again, taken in the 1995 field trip. And you can see the largest feature is that one on the right-hand side with everyone sitting on it, standing on it. It's probably, 2 metres, that's all. This site was looked at by Richard Anson, who did a PhD in the early 90s on this area. And this is just some from his thesis. You can see a couple of, on the left-hand side is a drawing showing the multiple landslides, mud flows on this slope. And from the cross-section, you can see there's nothing actually there that's any more than about 4 metres deep. And this is my map, made in 1978. You can see there's quite a lot of action in the area of the Soapers Wood field. I don't expect you to actually read all the information on this map. Hawkins showed this map to Skempton. He thought it was pretty good, so if it's good enough for Skempton, it's good enough for me. So, and I would like to point out, it's actually done the hard way. You know, this is pure artisanal graft here. This is none of your computer rubbish. You know, you've got tracing paper, you've got mapping pens, you've got ink, you've got stencils and all this sort of stuff. There's no Control Z if you make a mistake. You have to scratch the ink off with a scalpel blade, hope you don't go through the plastic. If you could afford it, there's things like Letraset and Letratone, but way beyond the financial means of a mere graduate student. So anyway, if you take the map, you scan it, you put it into a GIS, georeference it, and stick it over the photo, which is a little bit of modern tech that I didn't have then, you can see that the gap in the map is exactly where the wood is, no surprise. It's a bit of a shame, because when you go in the wood, there's a lot of stuff going on. Some quite big mud flows in the wood, knocking the trees over, doing all sorts of interesting things. But you just can't find your way around. You can't even move about through most of it in this vegetation. So it's blank on the map. Even Anson and Hawkins, when they published a sort of reconnaissance map, didn't give you a lot more information. It said clay slips in Soapers Wood, shows a little slip scar at the back, and a nice big couple of mud flows coming out of the northeast, and the hummocks that we've seen on the southern field. So what's the answer? Well, it's LiDAR. Again, not an ultra-modern technique, been around for a number of years, and it's actually Malcolm Whitworth who suggested I play about with LiDAR. This is what's called the digital surface model. It's the first reflections back from the laser. And so you can see the ground surface very well in the open field, so you can really see the detail of all the little mud flows in the two fields. But the wood is still the wood. Now keep your eye on the wood. When I press the button, the wood disappears. Now this is much better. This is what's called the digital terrain model. Now this is another set of data that you can get from LiDAR. You don't have to do anything to it. You buy it like this, or you download it for nothing like this. And what you can see is all the mud flows in the wood. You can also see a number of linear features that I never realised they were there. One of them might be this back scar, but is that a row of gulls or whatever? You know, I don't know. Interesting to go back and have a look. So if you put my map on the top in the GIS, you can see it would be very easy for me now, if I could be bothered, to actually fill in this map and finish it off using the data from the LiDAR image. And something else I tried, never completed, it was just a pain trying to draw this map by pen. There are some advantages to filling by AutoCAD. This was a slope angle map that I tried, and it wasn't getting anywhere, didn't really show much. But with the LiDAR data, you can actually produce a slope angle map with a few clicks of a mouse. And it's very good. You know, you can adjust it whatever you like. You can change the sun angle, all sorts of things. And I think you'll agree that the LiDAR map is probably a little bit better than my effort. Certainly an awful lot quicker. So now I want to basically turn to these deep-seated failures. So we've got these two here. They're written up in the QJGH, and they're also in this Glossop volume that Jim Griffiths has edited. And the first one's Balebrook. Now, if you look at Balebrook, you can see it on the Ordnance Survey map because there's a really big back scar that's wooded. But the area below the scar, the slip mass, is all part of the development of Bath Eastham. It shows up very well on the geology map. When you look on the aerial photo, you can see all the development, you see the houses, a lot of gardens, private gardens. There's also some open ground, but most of that tended to be things like market gardens and small crop fields, and it had been ploughed, I think, over the years. So when you draw the geomorphological map, you can certainly see the back scar. You can see some information on the disturbed mass, but there's an awful lot of white space, particularly down by the road and between the road and the railway. I just didn't even bother to go there because it was just impossible to get in. You can see actually these are the outlines of the potential routes for the A46, and the one I liked the best was the one that went in a huge viaduct across the top of this landslide and flew over the River Avon. But when you look at the air photo, you see they chose a boring route that went through the edge of the town. But the point about putting this picture on is that you can see the map and the picture together. You can clearly see where all the development has hindered the mappings. So you slip to LiDAR, now look at that, now that is what I call a landslide. You can really see the back sky, you can see how it comes round at the corners, you can almost see it going down to the river. It's quite dramatic. And you can also see quite a lot of detail, despite all the gardens. When you're zooming out of this level, you can see the detail in the texture and the shape of the land units in that disturbed mass. The slope angle map looks the same, not wonderful, I think, mainly because you've got one steep slope and lots of shallow slopes, so there's not that much contrast in it. But it is useful if I put the map back over the top of that. I've highlighted in these little green circles where you can see the missing data. And again, it would be very easy to update this map, get an awful lot more information from this modern technology than you can knocking on people's doors and saying, can I have a look in your garden for landslides? Which doesn't get you very far. Now the other one, North Stoke, that's just around the corner, a few miles away. Very similar geology, very similar size. Again, you can see a hint of a wooded back scar on the Ordnance Survey map. When you go there, most of the land is pasture, it's not been ploughed up. And when you do the geomorphological mapping, you get a very good map. There's a lot of information on it. You can see everything there. So the LiDAR looks like that. Again, you can see quite a lot of information from modern day techniques, but if you drop the map back over the LiDAR, particularly the one on the right-hand side, you can see that there's not actually a lot more information that's coming to us from the LiDAR, but certainly the LiDAR is an awful lot quicker to produce than stomping in the fields. So what else can you do with these digital layers? Well, if you use some sort of data visualization software like Surfer, you can actually use the 3D LiDAR to give you a 3D oblique image, as on the bottom left-hand side here. So you can create a 3D model, and then you can stack over it all your different layers. And I've got a couple here, plus the contours, which I've derived from the LiDAR, plus my original map, which is digitized and geo-referenced. And then you can just drape whatever layers you like over the 3D model, as in the right-hand side picture. So if you go back to Soper's Wood, here's the Soper's Wood 3D model with my map draped over it, and I've added contours from the LiDAR. Now this is very quick to do, it's very powerful. You might decide you don't want that, you want a colour picture instead. It's very easy, very good for presentation graphics. Which got me thinking sort of slightly tongue-in-cheek. I mean, why bother go out in the rain anyway, you know? And so here's the picture of the slip that I showed you from 1978. And the one at the bottom I've reproduced artificially from the digital information. And I've tweaked the sun angle to be the same as the real sun angle. I've changed the colour temperature in Photoshop so they're more or less the same time of day. I think you'd agree, it's not a bad match. What you can see is how far the mudflow has moved in 40 years down that slope at the bottom. But again, probably quite suitable for, desk study information. So what else can you do with with this. If you use ILWIS, which is another open source GIS system, you can actually import stereo pairs. And these are two photos, courtesy of Malcolm Whitworth again. These show an area of similar terrain, but in the Broadway area in the Cotswolds. You can see a number of shallow mud flows, and you can see also some medieval field systems at the bottom right there. But what this does, it allows you to produce an anaglyph view. So if any of you geeks have got your red-blue spectacles in your top pockets, now's the time to put them on, and you can actually see this in 3D. No one's got any. Useless. But it's much better than a standard sort of mirror stereoscope that you might have used in the past. And the advantage is that you can zoom in, you can move about with the specs on, and you can actually see the 3D stuff on the screen in front of you. And then you can actually digitize onto another layer. So you can just scribble with a mouse. Here I've started to put a few toes and a few scarps on it to give you a sort of feel for what you can do. And you could take this out, put it into a CAD system, you can leave it in the GIS, you can do whatever you like, but you can build up your ground model quite nicely with these electronic systems that I say are free to use. So I think I've proved that it is possible to teach an old dog new tricks. This is actually a real photograph of a dog-computer interaction experiment to try and stimulate the brains of old dogs, and I confess that I've given this old dog the Balebrook LiDAR to look at. But anyway, that brings me to lessons from the past. Engineering geomorphological mapping skills should not be forgotten, and they're vital. And here they are being taught to the MSc students at Portsmouth, so at least at Portsmouth they're getting a decent education. Again, harping back to the Cambridge conference, it was Jim Griffiths again who mentioned that these methods in the 1970s were advancing quite well, but since then they seem to have fallen out of use. And this certainly accords with my own experience. Of all the companies I've worked for, probably I was the only one who had the skills to do this sort of work. Even the last week before I retired from Hydrogeological, they had me out tramping the hills of Bath looking for landslides for a particular client. So I think new techniques, they are additional lines of evidence. You can go back, you can update your conceptual site models, I hope I've showed to you briefly here. But my advice is don't get carried away with it, and I think Johnny said the same thing, use the tech, but remember the basic skills. So that brings me really to the conclusions of this evening, and I just want to leave you with 4 thoughts. They are: to understand a site and predict how it's going to behave engineering geologically, a sound conceptual site model based on lines of evidence is essential. Secondly, multiple lines of evidence may be required to define a conceptual site model where there are challenging conditions or engineering requirements, or both. Thirdly, recognizing when a problem is complex is a key skill for engineering geologists, and only with in-depth consideration with sufficient resources of time and budget will that allow you to give suitable advice to your clients. Thank you very much for listening.